Okay, we're going to look at a few more examples of finding volumes by rotating two-dimensional planar regions to create a three-dimensional solid. Okay, so far we've used the method of disks and washers. Now what I'd like to do is just mix up a couple of problems and see if as we work through them you can make a determination for yourself which of the two methods we're going to choose to use. Okay, so the first example, as you can see on the screen, using the equations y equals x to the third, y equals 1, x equals 0, and then our rotation is going to be about the y-axis. So like all of our problems, we start by drawing a two-dimensional picture of what's going on. Y equals x cubed is just our basic disco curve. So a branch that, I guess a branch or an arm of the curve that opens up and to the right, and one that opens down and to the left. So this would be y equals x to the third. Y equals 1 is just a horizontal line through 1. And x is equal to 0 is just a vertical line through 0. So sorry, that one's a little bit tough to see because it's right on top of the y-axis. So our two-dimensional region then, guys, is going to be this one. And now our rotation is going to be about the y-axis. So we're taking that two-dimensional region and rotating it around the y-axis. I'm just going to, with a broken line, kind of sketch in a mirror image on the other side of the y-axis just to get a feel. And then when I try to make this look three-dimensional, then it would look just ballpark something like this. And the axis of rotation right through the middle, so something about like that. Okay, so my question to you guys is, when we make this three-dimensional by rotating that planar region around, is there a void or a hole in the middle of this? The answer this time is no, so that when I make any kind of horizontal slices, the slices then turn out to be disks. There's no hole, no void in the middle. Therefore, the shape that we create are disks. Okay? And so what we're going to need then is our formula for disks, which is pi times radius squared times height for the volume of each one of our disks. And then to calculate volume, we're going to add up all of the disks. Before I get myself started, I just want to use my laser pointer. H over here in my picture, H, the height of every one of our disks, vertical or horizontal, right? What's the height? Is it a vertical measure or a horizontal measure? I hope you can see from my picture that it's going to be a vertical measure. Therefore, the differential that we're going to use is dy. Okay? And then we'll have to multiply pi times the radius squared. And because our differential is in terms of y, our radius has to be in terms of y, and our limits of integration have to be in terms of y. Okay, now the limits of integration aren't too bad, I don't believe. Where's this bottommost disk going to be located? Well, if I transfer back to the two-dimensional picture, I hope you can see that the bottommost disk is going to be located at y equals 0. And where's the uppermost disk going to be located? Again, if I just transfer that back, I hope you can see that that's going to be at y equals 1. So using values off the y-axis, our bottom disk at 0, our upper disk at 1. So the only thing we're missing then, guys, is the radius. Again, going back to my laser pointer, trying to point at the radius over in my disk picture, right? Is the radius here vertical or is it horizontal? Is this radius vertical? Is it up and down? No, it's horizontal. And if it's horizontal, then we need to make sure that the radius reads or looks like x equals. Unfortunately, we don't have x equals. What we have instead for that equation is y equals. So I'll switch to red here and drop this down to where I have a little bit of room. And what I'm going to need you guys to be able to do is solve for x. Not very difficult. To get rid of a power of 3, we take the third root of both sides. So that x then is going to be equal to the cube root of y, or more preferably, y to the 1/3 power. So therefore my radius, which is horizontal, would then read as x equals y to the 1/3. Okay? And again, everything's in terms of y. Lower limit of integration was off the y-axis. Upper limit of integration was from the y-axis. Our radius for our volumes are in terms of y, and our differential, which is the height of our disk, is in terms of y. So that would be the complete setup. And I'm only going to perform one more step, and then I'll let you guys finish it off, and you guys can, amongst yourselves, compare answers. I'm just going to remind you to factor out a pi, just to get it out of your way so you don't get messed up with that. Just factor it out front. And then y to the 1/3 squared is y to the 2/3. And I'll leave the rest of the problem for you. Again, feel free to compare amongst yourselves as to what you get for the volume. You just have to use the power rule, add 1, divide by the new, and then apply F-tick, and you'll get the volume of that solid. Okay? Also, if you're still confused, if you don't want to communicate amongst each other, feel free to let me know, and I can post another video with the solution for that problem, or we can just talk it over on phone or by email, or if you guys want to try, like I said, that Google Hangout thing, feel free to let me know. Okay, but here's another example. Again, I'm just going to get to the same point for everybody. Start everybody off with some equations. The straight line y equals x, straight line x equals 4, straight line y equals 0, and the rotation that I'm going to ask you to use on this one is the y-axis. So I'm going to ask you to rotate about the y-axis. Okay, so again, start by drawing yourself a picture. So y equals x is just a straight line that goes through the origin that has a slope of 1. So that would be y equals x. X equals 4 is a vertical line through 4. So it would just be a vertical line through 4. And y equals 0 is a horizontal line through 0, which is again kind of hard to see because it's on top of the x-axis. So the two-dimensional region this time that we would get would look something like this. All right. And then the rotation we want to perform this time is about the y-axis. So we're going to rotate that two-dimensional region around the y. Again, I always like getting a mirror image on the other side to kind of get a feel for what this looks like. All right, so there's kind of a mirror image of the two-dimensional region on the other side. And then if I try to make this look three-dimensional, I'll just do the best I can. Feel free to chuckle. And then the axis of rotation goes right through the middle there. Okay, so that's probably about the best I could do to make it look three-dimensional. So again, it's kind of a strange looking funnel type picture. Okay, and if we were to perform horizontal slices on this. If you use vertical slices, that's fine to try, but it's really, really complicated as to how you would add up an infinite number of those folks. But if you try using horizontal slices, every one of the horizontal slices would be what type of shape then? Well, if I choose my laser pointer over here, when we take this two-dimensional region and rotate it around the y-axis, is there going to be this empty space in the middle? Sure. So that when we form our three-dimensional solid, this whole middle section is not there. It's gone. There's nothing there. It's a hole. It's a hole. There's nothing there. Therefore, the shape that we'd get when we take any one of those slices is going to be a washer. Right? It's going to be a washer because this whole middle section of the solid is empty. And therefore, what we're going to need to consider is the distance from the axis of rotation to the outside of every one of the washers. We call that capital R. And the distance from the axis of rotation to the inside of every one of those washers, that's little r. As always, we're going to need to consider the height. All right, and the question is that height vertical or horizontal? Well, in this case, that height is vertical, which means this is going to then become the differential dy. And therefore, our volume that we're going to calculate is going to be a definite integral with a dy on the end. So the rest of our working formula then is pi times big R squared minus little r squared, and then the height. So we need to know what capital R is, we need to know what little r is, and we need to know the limits of integration. Again, because the differential is in terms of y, everything has to be in terms of y. So how about the limits of integration? Well, our bottommost washer, the one at the very bottom of our picture, would correspond to y equals 0, and the topmost washer would correspond to what? What number on the y-axis? Well, there's nothing obvious that's here, so if I switch to red so I can get you to observe, what I'd have to do is figure out where this topmost washer is going to be located. Where would that be? Where would that location be? Let me make a better question mark. There we go. Where would that location be? Well, because y equals x, because that's our straight line, and because we're using the line x equals 4, when x is equal to 4, what's y going to then be equal to? 4 as well. So our lower limit of integration is going to be 0, and our upper limit is at 4. Please notice both of those were off the y-axis. Okay, now capital R again is the distance from the axis of rotation to the outside of our washer. Is capital R vertical or horizontal? Vertical or horizontal? Well, it's horizontal, so therefore we need something that says x equals. And do we have that? Do we have something that gets us, you got to be careful now, please watch, we got to find something that gets us from the y-axis to the outside of every one of those layers. Do we have something that says x equals that? Sure. And what is it? It's x equals 4, right? Because the outside layer, no matter where you're at, gets us to the vertical line, x equals 4. So we do have something that says x equals, therefore we can replace capital R with 4. Now little r is also going to be horizontal. So again, we want something that says x equals, and that's then going to be the distance from the y-axis to the inside of every washer. So this fella is capital R, this fella is little r. And do we have anything that says x equals for that? Sure, it's this equation right here, the very first one. It's just that you have to read it backwards. What's x equal to? Y. Okay, and there's our complete setup then for the volume. I'm just going to perform one more little step, but whoops, sorry about that. Just trying to shrink that up a hair. I'm just going to do one little thing. I'm going to remind you to factor out the pi, just so it doesn't get in your way. Then 4 squared is 16, and y squared is, obviously, y squared. And then I'll leave the rest to you guys. Integrate both of those terms, apply f-tick, and get your volume. Okay, so a couple more examples of finding volumes, this time using, well, I guess we're combining now. That I almost said just washers, but we're actually combining. And now using, you got to be good enough to draw a decent picture so you know whether you should be using discs or washers. So feel free to get after the assignment, see how well you do, and then feel free to contact me with any questions or worries that you have. Okay, there's going to be one more video that will go along with this section, but it's going to be an extra credit problem. If you wish to challenge yourself, feel free to give it a try. Okay?